Hey guys, James here, and today I'm going to be doing something a little bit different. So welcome to my little video about probability. First off, I'm going to go over one of my favourite practical uses for knowledge of probability, and then I'm going to go over two quite famous probability puzzles with hopefully a bit of an original outlook. So first off, one of my favourite uses for probability is poker. I absolutely love the game. If I had more free time, I'd be playing it a hell of a lot more than I do, and probably making some fairly decent money out of it. It combines luck with skill, and it really is a great game. If you haven't played it before, I would highly recommend it. I think it would be downright impossible for a decent poker player to not have at least a fairly decent grip of probability. So imagine yourself in the following situation. Even if you've never played poker before, hopefully from how I describe this, you should be able to work out what the best possible thing to do is. So you've got an 8 and a 9, and there's 4 cards which have been drawn out. There's one final card left to go, and if that turns out to be a 7, then you've got a 5-3-9 straight, which is the best possible hand in this situation, which means that if a 7 comes out, then you've either won or you've drew, and you can go as crazy as you want in the final betting round. There's 550 in the pot, and the second player has bet 50. You can either fold, or you can put in 50 yourself and go through to the final betting round. So is it in your best interest to actually play? I'll give you a few seconds to pause the video and decide for yourself then, and then I'll continue and show you what you should do and why this is the case. So it turns out that you really should bet in this round. There's 52 cards on a deck, and there's 6 cards visible, which means that there's 46 unknowns. There's 4 outs, which are the 4 sevens, which you need to win the hand. So 46 divided by 4 is 11.5. So as long as the pot is going to be more than 11.5 what you have to bet, then it is in your best interest to play this hand. 550 plus the 50 which the second player has bet will give you 600, and 50 times 11.5 is 575. So in this situation it's definitely in your best interest to play. Onward then. Puzzle 1, Game Show. Now this is a very, very famous probability puzzle. It's been mentioned in a couple of films, and I've heard many people try to explain this. But they've generally done a pretty terrible job, so hopefully I can do a little bit better. Imagine yourself in this situation. You're on a game show, and there's 3 doors presented to you. Behind one of the doors you're told is a car, and behind the other 2 there's a donkey. After you choose a door, the game show host will then open one of the other wrong answers, and you have to decide whether you should switch or stay. So you choose a door, and you end up in this situation. The game show host opens the other door with the donkey. Now, unless you're you, James 1978, you're probably going to want the car and not the donkey. So, is it in your best interest to stick or switch? So you can either stick to your original choice, switch door, or it doesn't matter because it's the same odds. I'll leave the video paused for a second then, so pause the video and pick your choice. So at the beginning then, there's a 1 in 3 chance that each door has the car behind it. So once you've chosen, you've got a 1 in 3 chance of that being the correct answer, and the other 2 doors between them have a 2 in 3 chance. So there's an absolute certainty that one of the other 2 doors has a donkey behind it. So once the game show host opens the door, there's a 0% chance that the door with the donkey behind it has the car, which means that there's a 2 in 3 chance that the other door has a car behind it. So it is always in your best interest to switch. Now, this can be a bit difficult to understand. Even some very, very intelligent people I know just can't seem to get their heads around this. But even if you don't understand the maths, you can test this idea out yourself. If you have a deck of cards, just use 2 number cards and 1 picture card, and try this idea out with a friend. Even if you can't grip the maths, after you've done this 10 or 20 times, you can be pretty certain that I am in fact correct in this. Question 2 then, virus. A new virus is discovered which affects 1 in 10,000 people. A scientist creates a test for the virus which is 99% accurate, regardless of whether or not you have the virus. You take the test and to your horror, the test turns up positive. So what is the chance you actually have the virus? Again then, I'll give you a second to pause the video and come up with your answer, and then I'll continue. So it's quite likely that you've written 99%. Wrong. The correct answer is actually less than 1%. So why is this? Let's examine it a little bit closer. So out of 1 million people, 100 will have the virus and 999,900 will not. Out of the 100 people with the virus, 99 will show up as positive and 1 will show up as negative. Out of the 999,900 who don't, 989,901 will show negative, but there will still be 9,999 which will show positive. So you're far more likely to be in the group of 9,999 who are given a false positive than you are to be in the group of 99 who are correctly diagnosed. The good news, however, is that if you're given the all clear, there's only a 1 in a million chance that you'll actually have the virus. So you might well be thinking, yes, this is a clever little question, but surely this situation is purely hypothetical and doesn't have any real-world relevance. Now, there was actually something quite similar fairly recently. Scientists came up with a test for autism, which was accurate up to 90% for diagnosing people with autism, and it would give a false positive 21% of the time. Now, this was a fairly small clinical study, only involving 40 people, so I wouldn't say it's that statistically relevant anyway, but let's suppose that their figures are accurate. Let's assume we test 150,000 people, and 1 in 150 people has autism, or whatever the latest figure is. So using their highest figure of 90% detection, out of the 1,000 people with autism, 900 will be diagnosed as such. And using the 21% figure for false diagnosis, out of 149,000 neurotypicals, 31,290 will be falsely diagnosed. So you're far, if you come up with showing signs for autism with this test, you're far more likely to be in the group of 31,290 than you are to be in the group of 1,000 people with autism. The good news is that if the test comes back negative, there's a 0.067% chance that you actually have autism. But if you do get a positive result, there's still only a 2.8% chance that you actually have it. Understanding probability, I think, is very important if you're to be able to determine why statistics can be misused and to avoid some very, very common pitfalls. So thanks for watching, guys. Comment, rate, subscribe, and I'll see you soon. Bye.